So this is Factorial trailing zeros, Leetcode 172. And the question is, given an integer n, return the number of trailing zeros in n factorial. So in an example like, say we have 3 factorial, which is 3 times 2 times 1, and that gives us 6. And in this case we have no trailing 0 and we would return 0. In the case of 4, we execute 4 factorial, which is 4 times 3 times 2 times 1 equals to 24. Also no trailing 0. And in the case of 5, we execute 5 factorial, which is 5 times 4 times 3 times 2 times 1, which would be equal to 120. And in this case we would return 1 because we have a trailing 0 here. The most intuitive way would be to attempt to somehow compute the factorial and then like count the trailing zeros through some like while loop or something, but that would be a bit slow for the purposes of this question. Like Leetcode would not accept that because it's too slow. So a better way that we could approach this is to really think about what creates a trailing 0. So why does 5 factorial have a trailing 0? We need to understand that to have a trailing 0, we need to somehow have a number that we multiply by 10. So in the case of 5 factorial, it's equal to 5 times 4 times 3 times 2 times 1, which can also be seen as 5 times 2 times 3 times 4 times 1. And if you notice here, 5 times 2 is equal to 10, so we could replace this with a 10, and this is why we have a trailing 0 here. And in the case of 4 factorial, 3 factorial, we don't. And the reason why it starts with 5 factorial is because the factors of 10 are 5 and 2. So these are the only two numbers that can create 10 when multiplied together, and 5 factorial just happens to have both of them. So since 5 factorial has those numbers, 6 factorial, 7 factorial, and greater numbers would also contain 5 and 2 and would similarly have trailing zeros. So now that we understand that we need to multiply a given number by 10 to have trailing zeros, how do we count them? We could count these zeros by using a little trick where we essentially divide whatever number given. So we are given a number n, and if we divide n by 5, then we would have the number of times that 5 goes into n, and for every 5, so let's say the number of times 5 goes into n, and for every 5 there is a existing 2 because 5 is greater than 2. So so we could use this to kind of count. Okay, so we have this number of 5s, and since 5 is greater than like 2, for every 5 there must exist 2's trailing behind, which when multiplied equals 10. But this doesn't take into account the case of like the squares and cubes of 5, like 25 is equal to 5 multiplied by 5, and if we were to just return n over 5, it wouldn't take into account the other 5 being made. So we also need to divide n by 25 to account for the extra 5 being made. And similarly, we would need to divide n by 125 depending on the number. So for numbers less than 125, we would end up getting n over 125 to be equal to 0 when rounding down, and that's exactly what we would need. So how do we approach this? We could approach this by, let's say the function name is trailing zeros, and we take in an integer n. We return an integer with the number of trailing zeros. We could go if n is less than 5 as a base case. Return 0. Then we could go int count is equal to 0. Then we could create an integer num equal to 5. And the use of num is to divide n at every point in our upcoming loop. Wow. So while n is greater than or equal to num, we could go count plus equal to n over num. So this essentially finds out the factors, like where I explained, where we go n over 5 and we keep track of those factors. And we would also want to go n over 25 and so forth till the value of n is greater than our divisor, I guess. So in this case, 25. And we could go num times equal to 5. And we could return count. So we keep multiplying num by 5. So here we could get the square, cube, 4th power, 5th power of 5s. And until n surpasses this, we would be fine. And n over num here automatically gets the floor using C++, which is what I write in. And so yeah, this is the Factorial trailing zeros Leetcode 172 using C++. Thank you. Like and subscribe, please.